Now that we've spent some time looking at how to verify a trigonometric identity using the information we already had, such as reciprocal rules, the Pythagorean, the quotient, information you already learned in previous sections, in these next couple videos, I'm going to introduce you to some new formulas and how to apply them. The first set that we're going to look at in today's video are called the sum and difference formulas. The sum and difference formulas will be sometimes used to verify, as you'll see, but mostly what we can do with these is get exact value of trigonometric of angles that are not exactly pi over 3, pi over 4, pi over 6, pi over 2. So we'll get to that in a minute. Let me introduce you to the formulas first. So let's look at our sine. I'm going to use alpha and beta. So basically, the sign of adding alpha and beta together is the same as taking sine alpha, cosine beta, and adding it to cosine alpha, sine beta. Now, the difference formula is a little different. The sign of subtracting alpha minus beta is now sine alpha cosine beta minus cosine alpha sine beta. So you can see that the sum and difference of angles, then when you take the sine of them, you are simply adding, and then in the difference you're subtracting. So there's really not a lot of difference between those two formulas. It makes sense. Cosine's a little bit different. Cosine of alpha plus beta is actually cosine alpha cosine beta minus, here that's opposite from what you're doing, so the sum of the two angles you actually have to subtract. And then it's sine alpha sine beta, and of course then cosine of alpha minus beta is cosine alpha cosine beta plus So I actually give these to you on a formula sheet so you don't have to go through the process of memorizing. And since you don't have to go through the process of memorizing, what I would really do is spend time on this video going through a couple examples. But before we do that, let's throw the tan in there. Tan is a little different. Tan of alpha plus beta is actually tan alpha plus tan beta over 1 minus. And tan of alpha minus beta is tan alpha minus tan beta all over 1 plus. So in the past, we certainly used to make students memorize these formulas, but since we're not, we will make sure we jump up to the correct formula when we need it. Okay, so what do these sum and difference formulas help us with? So, for example, suppose I wanted an exact value. When I talk about exact value, that usually means you can't just plug it into your calculator, because your calculator will usually, depending on the calculator you have, just yield you an approximation. So when we say exact value, that means we expect to see you apply the formulas above, or the formulas in any of these videos in this section. So suppose I wanted the exact value of, let's do cosine of 7 pi over 12. Well, what you need to do is think about how can I take 7 pi over 12, break it into two angles where I either add those two angles to get 7 pi over 12 or subtract them to get 7 pi over 12. Now, because they need to be angles that I can easily get the trig identity of, the angles that we want to work with are going to be angles such as pi over 6, pi over 4, pi over 3, pi over 2. And then any angle that has a reference angle. So what do I mean by that? Well, 5 pi over 6, 7 pi over 6, right? 3 pi over 4, 5 pi over 4, 2 pi over 3, 4 pi over 3, and so on, 3 pi over 2. If you can get 7 pi over 12 as a combination of any of these angles, you can apply your sum and difference. So you're like, all right, well, how do I do that? Well, you look at your denominator. Your denominator is a 12. Well, a 12, to get a common denominator of 12, all you need are two fractions that have 12 as its common denominator. So in other words, 3 and 4, 6 and 2. So because it's over 12, if you're really not sure and not seeing it, what I would probably do is take these and put them over 12. So for example, I want to make it a common denominator of 12. Oh, well, pi over 6 becomes 2 pi over 12. Pi over 4 becomes 3 pi over 12, right? Because 3/12 reduced to 1/4. Pi over 3 becomes 4 pi over 12, and that becomes 6 pi over 12. Okay, so I look at these variations of pi over 6, pi over 4, pi over 3, pi over 2, and I look at them and say, hey, do any of them either give me a sum or difference of 7 pi over 12? And if, now clearly they do, you got your 3 pi and 4 pi, but if they don't, you can then go to this next set and put them over 12. So for example, you have 10 pi over 12. You've got 9 pi over 12. All right, you got 8 pi over 12. So there's different things you can do to attempt to get to that 7. But we have that 7 right here. All right, once you do a few of these, you'll easily be able to break up your angles. So what does that mean? Well, I'm going to let alpha be 3 pi over 12 or pi over 4, and beta be 4 pi over 12, which is pi over 3. And I'm going to take 7 pi over 12. I'm going to say, well, wait a minute. 7 pi over 12 is the same as 3 pi over 12 plus 4 pi over 12. Well, that's the same as pi over 4 plus pi over 3. So in other words, cosine of 7 pi over 12 becomes cosine of 3 pi over, not 3 pi, sorry, of just pi over 4. You want the reduced angle, plus pi over 3. You see that? By doing that, I can now apply, remember that's alpha and that's beta. I can apply this formula right here. So when I break that up, what I'm taking is cosine of pi over 4. Take a look. Cosine of pi over 3. And nope, it's minus. See, you reverse it with cosine. Minus sine pi over 4 sine pi over 3. Well, why is that helpful? Because I can get the trig functions of, let's do my pi over 4 first. I know pi over 4 goes 1 square root of 2. And pi over 3, which we know is the larger angle, right? So pi over 3, that's a 60-degree angle. That's the larger one. So the 1's there, the 2's there, square root of 3. So as long as you know those angle relationships with your 30, 60, 90 and your 45, 45, 90 triangle, we can work this. So I refer to my triangles. Cosine of pi over 4 is 1 over square root of 2, which we know rationalizes square root of 2 over 2. Cosine of pi over 3 is 1/2. It's adjacent over hypotenuse. Sine is also square root of 2. Cosine and sine of pi over 4 are the same thing. But sine of pi over 3 is square root of 3 over 2. Now again, we are working with exact answers we want. We only want exact values, so I cannot plug any of this into the calculator. I'm going to get square root of 2 over 4. I can square root of 2 times radical 2 times radical 3. They're both under a radical. I can make that radical 6. Because they have the same denominator, I can write that as square root of 5, square root of 6, square root of 2 minus square root of 6 over 4. And that is my answer. And that is considered an exact value. Your calculator, of course, would give you a much different answer, version of the answer. So, you know, to do this, you do have to be able to look at a fraction or look at an angle that's in radians, a fractional angle in radians, like 7 pi over 12, and determine how can I rewrite that as one of these common reference angles that I know how to work with. So that's kind of the idea. So you will need to kind of play around with that. And we can look at another example in degrees. So maybe if you're not quite understanding the radians, what if I wanted the exact value of sine of 105? Now again, I know you can plug in sine of 105 degrees. Put your calculator in degrees and get that, but that's going to give me an approximation. I want the exact value. So now I need to think about, okay, but I'm in degrees. I don't need to be in radians. So what are my angles I can work with? I can work with 30 degrees, 45 degrees, 60 degrees, 90 degrees. And we can do different variations of that, like 135, 120. Because we can do 180 minus 30, 150. 180 minus 45, 135, 180 minus 60. And we can do all sorts of different angles to get to 105. Because sometimes you have to subtract. Sometimes you have to add. And very often there is more than one way to get an answer. So for example, 105 could be 150 minus 45. That would work. Or 105 could be 60 plus 45. So there's usually more than one way. The reason I would go with this one is because they're both reference angles under between 0 and 90 degrees. the 150, you have to be careful of the quadrant and actually use the correct reference angle. So we can go with this one and say, hey, I can rewrite 105 as 60 degrees plus 45 and go through using the sine formula. So I have sine 60, cosine 45, plus cosine 60 and sine 60, well, we kind of had it up there because pi over 3 is 60 degrees, the square root of 3 over 2. So this one is square root of 3 over 2 times square root of 2 over 2. You can put your angles together. Cosine of 60 is 1/2. And sine is square root of 2 over 2. So you end up getting square root of 6 plus square root of 2. Whoops, that's over 2. Over 4. As your answer. Another type of example you will see with these problems is if given. So let's suppose we are given an alpha and a beta. And let's say alpha is equal to 12 over 13, and you need to be told what quadrant alpha is in quadrant 2. And beta is 3/5. Sorry, I forgot the sign. Put your sign there, sine alpha and sine beta. Forgot to say that part. That was pretty important because the sine is a ratio, and that's in quadrant 1. So sine of alpha is 12/13 in quadrant 2, and sine of beta is 3/5 in quadrant 1. In this particular instance, you are not told what alpha and beta actually are, and that's okay. Okay, from here, we can do various things like, hey, what if I wanted the sine of alpha minus beta? Well, I can get the sine of alpha minus beta by drawing each of these. So let's draw alpha here in quadrant 2. It's given that it's in quadrant 2. It's 12 over 13, so here's my alpha reference angle, and that's going to be 12 over 13. Now beta is in quadrant 1, so that's beta. It's not a reference angle in quadrant 1. And sine of beta is going to be 3/5. But we're going to need also cosine of alpha and beta. So to get cosine of alpha and beta, you're just going to need to use your Pythagorean theorem. And to use Pythagorean theorem here, we get 169 minus 144 is 25, so that's 5. It's also a very common triple. And then here it's a 4 because it's 25 minus 9, which is 16. Square root of 16 of 4. Again, a very common triple, right? Yeah, 169, right? 169 minus 144 is 25. Square root of 25 is 5. All right, so we have all our information. Do make sure you put in your plus and minus. We're fine with beta because beta is in quadrant 1, so we didn't have to worry about that. But take a look at that alpha angle. Alpha is in quadrant 2. The 12 is positive. It's given to us as positive 12 over 13, the sine, so we know sine is positive in quadrant 2, but that is a negative value. We know that by looking at it on the graph. And this idea that cosine, of course, which would be adjacent over hypotenuse, is negative in quadrant 2. So do take the time to put those negatives and positives in if they are needed. Now we can just simply apply our alpha minus beta formula, which is this second one right here. So sine alpha cosine beta minus, so let's start with that. So we have sine alpha cosine beta minus cosine beta sine alpha. Now here's the cool thing, we have no idea what alpha and beta actually are, and that's perfectly fine. We don't need to know what alpha and beta are, because I can go right to my pictures. Sine of alpha, well, that was 12 over 13. It's given in the problem also. Cosine of beta, just, it's like doing a little key here, like a map. Go to beta, take cosine of beta, and that's going to be 4/5. Now, cosine alpha, I know some of you are saying, you put them in the wrong direction. I did. It's okay. I fixed it. Cosine alpha, when I followed the formula, I mixed up my alpha and beta. We'll double check. See, look at the formula. It's sine alpha, cosine beta, cosine alpha, sine beta. I mixed it up. All right, so stop, fix that. Now, cosine alpha is that negative 5 over 13, and sine beta is 3/5. So 12 times 4, that's 48 over 13 times 5. I'm not going to attempt that in my head because I will probably mess it up. So go ahead and get 13 times 5 just to make sure I got that right, 65. The negative minus the negative that's going to end up over here is going to cause that whole thing to be. So 48 plus 15, of course, is going to give us 63 over 65. So that's just the types of examples you will come across. Now we could also see a verify identity with any of the new formulas you're learning here. The directions will explicitly read verify each identity. So here's one. Let's verify theta plus pi over 4 equals cosine theta minus plus sine theta, sorry. Let me make sure I copy it correct or I'm not going to be able to do it. Cosine theta So very often if you're asked to verify an identity and within parentheses you see angles being added together, that's kind of a key to tell you to go to one of those sum or difference formulas. So tan of alpha plus pi over 4. Let's take a look up at our tan formula. Ooh, we have this formula right here. So what we're going to do is replace tan of alpha plus beta with tan alpha plus tan beta, 1 minus tan alpha tan beta. So we're going to have tan theta let's double check, make sure we got it right. So tan alpha plus, so tan of, or in our case it was theta plus tan of pi over 4 and 1 minus. And this is what we need to get it to look like. So let's play around with our left-hand side here for a little bit before we start looking at that right-hand side. Oh, so tan of pi over 4 is tan of 45 degrees. We know that's a 1. So now we have tan theta plus 1 over 1 minus. tan theta. Well, we need to get this to look like that. So there's a couple things you can likely do here. There's probably more than one way to work this problem out. One of the things we can certainly try doing, which I think will work nicely because we already have the plus in the numerator and the minus in the numerator. And that is to, whenever you see one side in tans and the other side in cosines and sines, just change your tans to cosines and sines. All right, so I'm going to move this up a little bit and we'll look at that right-hand side when we're done. So what does that mean? I'm going to change this to sine over cosine. Okay. And then I'm going to get rid of that complex fraction by multiplying everything by cosine theta. Just to get rid of, so if I multiply everything by cosine theta, my cosine theta goes away. I distribute it, right? Because cosine theta over cosine theta is just 1. So I'm going to distribute it across the numerator. The cosines are going to cancel, and I'm going to have sine theta plus cosine theta. Cosine theta times 1 is cosine theta, cancel, minus sine theta, and there it is. It's exactly what we have. I mean, the cosine and sine are reversed. This is what my left-hand side looks like. This is what my right-hand side. I'll bring it down now. That's exactly what it looks like. And that's okay because we can, because this is an addition, I can just switch these. I don't need, you know, you can't switch them if there's subtraction, but we don't need to switch them. Now I can say that, yes, they are indeed exactly equal to each other. Verified. So again, when you are looking at verifying something and you see a trig function with this plus and minus of two angles, you probably want to use one of these identities. And you would state that in this step, you would just state that you used the sum identity for tan, right? And then here, we used our reciprocal identity. So remember on the test, you are going to want to give which identities you used when solving these problems. And that's it for sum and difference.